Cofactors. Sounds cool, and it is cool. All right, cofactors. So this is another way of computing determinants, which will be of most use for us. Well, lots of places, but we're particularly thinking about computing eigenvalues and eigenvectors. But there are more uses, of course. All right, and we'll show some very surprising things that come out of this. So the way of the cofactor. So it's going to be a recipe. I'm just going to tell you how to do it. This can all be explained or connected to by the three basic rules of what determinants need to do, how they need to behave. Once again, those things are that the identity matrix has a determinant of 1. If we swap any two rows of a matrix, then its determinant changes sign, and determinants are multilinear in their rows. Awesome. Everyone is thrilled by that, I know. Okay, so yes, this is actually a card table. Welcome back to the matrixology card table. I like it. Yeah, so let's see. So that's going to be a big thing, right? So we want a really clean way to find determinants because the eigenvalue problem is a bit nasty. We showed some examples where if you try to compute with row operations, you end up with a bit of a mess. So, and that is true. So this is going to be a kind of a nice, lots of symmetry involved sort of approach. So, okay. So row operations were really crucial in showing all those results that we found for determinants, right? The determinant of the product of two matrices, the product of the determinant of A is the same as the determinant of U plus or minus. It's a product of, and the product of the pivots. Determinant of an inverse is the inverse of the determinant, all sorts of good things, right? So they came out of using row operations and understanding that they followed, that they were things we could use based on the first three rules of determinants. All right, so here's the story for determinants in general. So if you've got an n by n matrix and you're trying to find its determinant, it can be seen as a sum of n minus 1 by n minus 1 determinants. So if you have a 3 by 3, it's a sum of 3 2 by 2 determinants. If you have a 7 by 7, it's a sum of 7 6 by 6 determinants. And so it's recursive. Right, each of those 6 by 6s has 6 5 by 5s, and so on and so on and so on. So that immediately sort of, at least saying that should indicate how nasty it is. There's sort of a factorial explosion involved. So we're going to work with this one example, a 3 by 3. We'll do a 4 by 4, work on a 4 by 4 as well. And that's probably enough. Okay, so yes. So this little beast here, 1 1 1 0 3 2 2 1 2, it's an innocuous looking thing, but we want to find what's the volume of the parallelepiped that these three vectors generate. Right? What's its determinant? So we're going to define a bunch of things here, work through it, and give you a procedure. So this is an Mij. It's the m minus 1 by n minus 1 matrix formed by deleting the ith row in the jth column, right? So there's I, j of A. I've got some examples here, but let's just quickly, so if we take out the first row, that will be I equals 1, and say the first column, that's j equals 1, we're left with these for this little 2 by 2 matrix. And there are n squared of these, right? So there are, because you just start at each point, so there are n squared numbers in here, in an n by n in general. So there are n squared of these, and we call them minor matrices of A. Right, so that's our first piece. We're going to build from there. So here's the example I just mentioned. So again, here's our matrix. Pac-Man is eating things in here. So take out the first row, first column, what's left? 3 2 1 2. Take out the first row and third column, that's M1 3, and we're left with 0 3 2 1. What happens if you take out something when you split it up? Well, so M2 2, so take out the second row, second column. You just delete them and then squish everything back in. So this is 1 1 2 1, 1 1 2 1. Cool.
All right, and if we took out, say, the middle column and the first row, we'd end up with 0, 2, 2, 2. They just vanish, they fold up. So you can imagine like that. You're just erasing it and then pushing all the numbers up, erasing the row, and then erasing the column, pushing all those numbers together. So Mij is the ijth minor of A. This is, so the determinant of the minor matrix, Ij, the determinant, right? Just to be clear, it's the ijth minor of A. So we've sort of shortened it, we've taken out the word determinant, it just has a special term. Yeah, and this is just saying there are 9 of these matrices for A, which sounds like a bad story, but it's going to be okay. For calculating determinant, we only need 3 of them at a time. Okay, so minor, so we've gone from matrix minor to minor. And now we do this extra step where we take the minor and we multiply it by -1 to the power of I plus j, which is going to seem like a bit of a funny thing to do. But it is a result of row swaps and column swaps, right? We're allowed to do column swaps now. It's a result of that in showing that a general matrix has this formula that we're about to derive. Okay. Okay, so you can think of this as a checkerboard of pluses and minuses. Right, so I plus j is even when that's even, so 1 and 1, 1 plus 1, that's here, we get an even number. When it's odd, we get -1. So that means we end up with a alternating, let me put in some more of this room, alternating sequence of I really like a card table, it's great. All right, yeah, an alternating pattern of plus and minus checkerboard, if you like. All right, okay, and we're going to call this thing the cofactor of A, and that's really the big deal. So these are some good names to have, and that's how we build it. Minor matrix, minor is the determinant of the minor matrix, cofactor is the business. All right, so it's just the same as this minor, determinant of the minor matrix, with this extra switch, which, as I said, counts for row flips, column flips. All right, good. So here's a theorem. We're going to just throw this out here. I think a webisode would have to be involved to explain this. Determinant of A is given by a dot product of A's, so we'll say this slowly, A's cofactors and A's entries. So it's a dot product, right? Classic dot product, along any one row or column. So we can take the first row of A, find the cofactor for C for position 1, 1, position 1, 2, position 1, 3, multiply those cofactors by these entries here, which are 1, 1, and 1, sum them up, that's what a dot product is, and that will be the determinant. We could go down the second column here, find the cofactors here, here, here. Cofactors are funny because they never involve the row or column you're in. They involve other parts of the matrix. But you'd have 1 times the cofactor for this position, 3 times the cofactor C2, 2, and 1 times the cofactor C3, 2. Add them up. Weirdly, all of these things will give you the determinant. This is Crazy Town Banana Pants. And it's a dream of Pac-Man. So this is just to write the formula out in a couple of ways. So we could go across the top row. So 1 and 1, row 1 and row 1. Across here, column. So J is the column index. So we're going 1 to N. So cofactor, entry of A. We could go down the second column. Cofactor, entry of A. Right? Doesn't matter which one. And so you see the indices have changed. This is an I now because I is a row index. So let's build this up slowly. Let's go across row 1. Let's see if we can do it there. Okay. Minor matrix 1, 1. It's 3, 2,
1, 2. Right? We're wiping out this row, this column. Minor matrix 1, 2. We're wiping out first row again, second column, so it's 0, 2, 2, 2, 0, 2, 2, 2. Then we are wiping out the last column, first row, 0, 3, 2, 1. It's this business here, 0, 3, 2, 1. All right, so now we've got them. Take their determinants. We know what they are for 2 by 2s. We'll come back to 2 by 2 determinants in a little bit. So 3 times 2, minus 2 times 1. So 6 minus 2 is 4. 0 times 2 minus 4. 0 times, so it's minus 4. And 0 times 1 minus 3 times 2, minus 6. And then, so that's the minor matrix, minor cofactor. So cofactor, we just take this number, multiply it by minus 1 to the appropriate power. Here it's 1 plus 1, here it's 1 plus 2, here it's 1 plus 3. So the only one that has a minus sign is the middle one, right? So minus signs are associated with this number, this number, this number, and this number for 3 by 3. So we're just multiplying by plus 1, minus 1, plus 1, so we get 4, 4, minus 6. So the minus went from 4 minus 4 minus 6 to cofactors 4, 4, minus 6. So the claim is then that the determinant of A is this dot product. This is a dot product. Right? It's C11 times A11, C12 times A12, C13 times A13. So if you like, it's the cofactor associated with the first row and the entries of A along the first row. So let's put them in. So it's all of the A's are 1 across here, 1, 1, 1, and 4, 4, minus 6. So 1, 1, 1, and 4, 4, minus 6. So we've got 8 minus 6, 2. So there's our determinant. All right? Good. Good. And that's what we found from before. Let's go back to this one. This is a previous installment. We did row operations on A and we got to 2. Right? You can see it's a different business. This is a much more funny looking thing here that we've done. But this is just doing row operations, blah, 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 blah. Stepping it down to until we get to the identity matrix. Good. So confirmation. So there's an as before, as for row ops. So now we can choose, we could have, according to this theorem, we can choose any row or any column. Not the diagonals if you're getting carried away with magic squares or something. That's not what we're doing, people. But we can choose any row. So let's do it kind of all at once. So that's the statement. We can choose any row or column. Let's do all of them at once. Crazy. Right, we're out of control here. So we'll create a cofactor matrix. So each entry of A has a cofactor associated with it. We've just computed 4, 4, and minus 6. And if you go through, you'll find these ones as well, right? So minus 1, 0, 1, minus 1, minus 2, 3. Right, so the cofactor associated with this entry has nothing to do with the 0. Take 1, 1, 1, 2. So it's 2 minus 1. That's the minor matrix. The determinant of that is 2 minus 1, which is minus 1. Sorry, it's 2 minus 1, which is plus 1. And then we need the power, which in this case will be like this. It'll be a minus sign, so we end up with a minus 1. All right, so you can go through and figure those out. Good exercise. I know you'd love to do it. So that's a very good thing to do, very healthy. All right. Now let's do a funny thing that we normally don't do with multiplying matrices together. We're going to take this sort of direct product of all the elements, because that'll allow us to then compute a whole bunch of dot products at once. So we're going to take all of A and all of C and then just overlay them on top of each other. And hopefully I've written this out clearly here. So it's 1 times 4, 1 times 4, 1 times minus 6. There's that. 0 times minus 1, 3 times 0, 2 times 1. That's all of this. And then 2 times minus 1 here, 1 times minus 2 here, and then 2 times 3 here. So it's not a normal matrix multiplication, but you can, this notation is fine. We're saying, multiply the ijth element of this new matrix is just the product of the ijth element of each one, A and C. And then this means create a matrix. All right, so we compute all these things. We have 4, 4, minus 6, 0, 0, 2, minus 2, minus 2, 6. So along each row is the kernel of a dot product, right? It's the, right, so there's 4, 4, minus 6, 4, 4, minus 6. And to finish the dot product, you just have to sum up the numbers. So let's sum them up. 4, 4, minus 6. So this is going along the top row to 2, which we already found, right, as above. Let's now do something where we would be effectively going along the middle row here. We get the inner product of, right, 0, 3, 2 with minus 1, 0, 1. So we get that. Sum that up. The dot product, if you like, 0, 0, 2, 2. Let's do the bottom row. So minus 2 plus 6, 2. And we can do by columns. 4 plus 0 minus 2, 2. 4 plus 0 minus 2, 2. These cancel, 2. That is inconceivable. All right, I'm giving you a method. We'll talk about it in another time as to why this works. But you know, the upshot is you don't have to calculate all of these, right? So, well, A, it works, and it's a very, it just involves products. There aren't things on the bottom. There aren't horrible denominators to deal with. And you can choose. So if there's a really, you know, nice looking row here, and I'll give you a reason, or column, I'll give you a reason for that on the next page. You can choose the best one. All right, so this is, or the easiest one, if you like. So rather surprising. The determinant is definitely 2. All right, so this cofactor method enables us to do very sneaky things, and we can save ourselves a lot of labor by choosing a row or column of A that has a lot of zeros in it. It's really just about the zeros. Excellent sneakiness. So this would be the best choice because it's 1 here, 0, 0. So if we go back to our calculation, here it is, good. If we go back to our calculation that was based on the first row, if this was a 0 and this was a 0, we don't even have to calculate the cofactors. So what we want to do is avoid, right? So there's no need to compute cofactors associated with zeros and A, right? So we're avoid trauma. Right, we're just de-stressing ourselves a little bit here. So yeah, the best choice is this. So 0 times, it doesn't matter what the cofactors are. We're just going to leave them out. So it's 1 times the cofactor associated with this entry. That's the determinant. So 1, here's the cofactor. It's minus 1, 1 plus 1. Determinant of the minor matrix, 2, 3, minus 1, 1. So it's 6. This is where people go wrong a lot, by the way. So it's 6 minus minus 1. It's easy to just subtract that. So that's a 7. So 6 plus 1. 1, 1, that's a plus 1, 7. Good. This one, we would choose, this example, we would choose the third column. It's got 2 zeros in it. So that's our best one. So we get a 2 for the entry here, and then we have to multiply by the cofactor associated with this point, which is row 2, column 3. So it's minus 1, 2 plus 3. That's our I plus j. This is cofactor 2, 3. So when we erase this column, this row, we end up with 2, 7, minus 1, 4. 2, 7, minus 1, 4. That's our minor matrix. Take its determinant, 8 plus 7. So it's a 15. And the minus sign is there, so it's 2, so it's minus 30. Okay. So that's much better. I mean, the worst thing we could do in these two cases is go along the bottom row. We'd have to calculate 3 cofactors. Here we'd have to calculate 3 cofactors. The others have zeros in them, which helps, but always fun. Choose the one with the most zeros. There's some other things, but that's a big deal. All right, let's just go back to 2 by 2s just for a little tiny bit of fun. So yeah, so let's see. We've got move this across. Yeah, A11, A22, A12, A21. So we're going to go along the top row here. That's what we'll choose. So it's A11 and A12. It's the dot product with C11 and C12. Cofactors associated with those points. What are those cofactors? Well, so it's -1 to the 1 plus 1. And if you cross out this row and this column, you're just left with A22. Determinant of a 1 by 1 is just that number. And over here we have A12. We cross out its row and its column. And we end up with A21. And there's a -1, 1 plus 2. So when everything gets cleaned up, we get this, that's just a +1. This is a -1. So it's A11, A22, minus A12, A21. So that is as we had before, right? So determinant of A, B, C, D is AD minus BC. Cool. So that's very nice. Very nice. So we didn't need to even know the determinant for a 2 by 2. We just needed to know the determinant for a 1 by 1. I know, it's great, so exciting. All right, let's do one more example. We'll do it for a 4 by 4, and we'll use more of the sneakiness. So it's this big blob here, 2, 2, 3, minus 1, 0, 7, 0, 0, and then your heart leaps when you see this. You're like, yes, yes, I am not forsaken. 0, 7, 0, 0, lots of zeros. You have a cunning plan. The other thing is that you might do one row operation as well. You can do that as well. You might find a big determinant, and you can see that adding one row to another or something might, here and there, just a few simple ones might create a whole bunch of zeros. So you can do a mixture, a blend of these things. And again, it could be columns. So this is a pretty good column. This is a grand one. So we end up with, doesn't matter what these cofactors are, because they're going to be multiplied by 0. So we just need 7 times its cofactor. And its cofactor is -1, 2 plus 2, right? Row 2, column 2. And what's left when we get rid of this row and this column? 2, 3, minus 1, and then -1, 1, 0, and 0, 0, 3. So now we've got a 3 by 3, which in principle could, could be full of numbers and bad, but gloriously we have zeros again here. There's a 0 here, but this is the best row, or the best row or column. So we'll choose that one. This is just +1, so we'll just let that go. 7 is at the front. So it's going to be 3 times the cofactor associated with this point. Now we're in this 3 by 3. We've forgotten about our 4 by 4, right? So all references are now to this matrix. It's a 3 by 3. It's in the third row, third column. So we get -1 to the 3 plus 3. Again, that's a +1. And if we wipe out this column, this row, we end up with 2, 3, -1, 1. Yep. Determinant of that is 2 plus 4. Sorry, 2 plus 3, which is 5. I think that's something else. 7 times 3 times 5. 105. MATLAB verified. It's true, actually. That is good. So starting with row 1 would have been painful. That would have been a bad plan. Or column 2, bad plan. All right, so you can see there are actually lots of puzzles built around determinants as well. I'm sure you would love to play with it. They are actually quite magnificent. All right, so cofactor method. This is how we do it. Let's go back. All right, minor matrices, minus, right, that's what you get when you wipe out row I, column J. The minor is the determinant associated with that matrix. The cofactor is simply that minor with this checkerboard -1, +1 factor. And then we get to this rather odd thing that the determinant is given by the product of the dot product or the inner product of a row of A and the same row of the cofactor matrix, or a column of A and the same column of the cofactor matrix. We did this little calculation where we essentially sort of overlaid them and showed that because there are 6 of these in general, there are 2n ways to attack it, right? So there are n columns, n rows. All of them gave the same determinant. Pretty spectacular. That gives us some shortcuts if we find zeros. And it also helps us, we even see that it works for 2 by 2. So that's the plan, yeah. So shortcuts when you have lots of zeros. If you need to do one step to make lots of zeros, or a couple, then you should do that as well. because row operations remain a tool that you have. All right, so that is how we compute cofactors, and how we compute determinants based on these strange beasts. So the next thing to look at will be Cramer's rule, and how that's a very odd thing, and how that gives you a solution to AX equals B and a formula for the inverse of A. All right.